Welcome to another video in the series about the C7000 compiler. This is the first of two videos that introduce a feature unique to C7000 called the Streaming Address Generator, including why and how to use it from the compiler. My name is George Mock, and I'm your guide. A streaming address generator reduces the number of instructions needed to compute an address for a load or store instruction. So this becomes important in a loop. By reducing the number of instructions in a loop, that loop runs faster. Well, how does this work and how do you program it? That's what these two videos are about. Throughout these two videos, the abbreviation SA stands for Streaming Address Generator. This is also true throughout the compiler documentation, application notes, and other things like that. An SA is a multi-dimensional offset computation engine. I realize that sounds a bit odd right now, but when we start going through the examples, trust me, it'll start to make more sense. Current C7000 variants provide 4 SAs. They are called SA0, SA1, SA2, and SA3. An SA can compute offsets for up to 6 dimensions, and it is used in combination with load and store instructions. This video, part 1, and the following video, part 2, each contain 2 examples for a total of 4. Each example builds on the previous one. Each example contains one function which sums an array of length integers and returns it. I spent quite a bit of time comparing the examples, and while that's happening, the older one is on the left and the newer one is on the right. Never hesitate to pause the video to closely view an example. Take screenshots, whatever you need to do to sort of slow down the pace that I'm working through the video, working through the examples. Some of the examples are really dense. There's a lot of code there. There's a lot happening. And so it's going to make sense to pause it at certain points. These videos presume that you understand the content of these earlier videos in the C7000 video series, and their titles are Vector Predicate Representation and Scalable Vectors. If something's going on that has you really deeply confused, the likely best thing to do is to go view these videos, and that's probably going to clear that up. Welcome to the first example. The purpose of this example is to establish a baseline for comparison to all the other 3 examples that are coming in this video and the next one. The interface for this function is shown here on line 3. It takes a pointer to a bunch of integers. Length is how many there are, and they're all added up, and that value is returned. All of the functions shown in this video and the next have this same interface. On line 5, this is how you create a variable that is a vector of 4 integers and initialize it to 0. On line 6, that's how you create a pointer to a vector of 4 integers and initialize it to PTR, which is the argument to the function that is passed in. And on line 10 is where there's a loop that is adding up all the pointers 4 at a time. Okay. On lines 14 and 15 is code that adds up the last few values in the case where the length is not an even multiple of 4. This is described in detail in the video titled Vector Predicate Representation. But briefly what this does is it develops this predicate, and then it uses this predicate in the select intrinsic to choose between values from here or 0 and add those values into sum_i4. This last loop here, lines 18 through 20, it's all scalar code adding up all the elements of the sum_i4 vector. Only thing that's a little bit interesting is this expression here is how you access one element inside the vector sum I4. And then, of course, it's returned. All this code here, lines 17 through 22, is very similar in all of the examples, and so this is the only time that I'm going to describe it. Next, I open up the second example. The purpose of this example is to introduce the SA interface for fixed width vectors, which is a great place to start, and then the following examples will do things in a bit more complicated way. Whenever we're looking at comparisons of code in this video and the next, the older code is on the left and the newer code is on the right. Next thing I like to do is to line up things that are the same to make the comparison easier to see. Okay. There we go. So, as I've said before, the interface to the functions is the same. So they both take, length number of integers and add them up and return that value. Both of these do it 4 integers at a time with vectors of 4 ints, but the one on the right does it with the SA, and we'll see what that means. Let's start by looking at the setup code. On the left, we include setting up a variable called pointer I4, and on the right, in the newer code, there is no equivalent. So what's going on there? That's something that will be explained. Looking at lines 8 through 12. This is the first of the SA interface code to consider. When you're going to use the SA, you have to configure it. And this is how you do it. What you do is you create a structure, and in this case the name of the structure is SA params. The type of the structure is this name here, SA template v1, and that type name is defined in the header file c7x.h. So here, okay, c7x.h is where that type name is defined, and all these other names that we're seeing here on line 9s through 12, all those names come from c7x.h. So we've talked about the structure, the type of the structure. You call this function gen SA template v1. That function creates a structure, populates with all the default values for configuring an SA. And then you return it here to SA params, and then on lines 10 through 12, we're changing the defaults for 3 of the fields in the structure. So the first one to talk about is veclen. That stands for vector length. How many elements are in the vector that we're working with in this particular usage of the SA? And in this case, it's 4 elements, and so you set it to this value. So it's important to realize that this 4 right here and that 4 right there match each other. That's where the 4 comes from, okay? So in line 11, we're initializing this field. That's shorthand for dimensional format. Now remember that the SA is an offset computation engine, and it can compute offsets for up to 6 dimensions. And so a question you have to answer, well, how many dimensions am I using this time? Well, in this particular case, we're using 1 dimension, and that's how you say that, okay? The next field is iCount0. You're telling the SA what is the total number of elements that we're going to work through in this use of the SA. And in that case, it's length, which is the very same length that is passed into the function. Okay? So up to this point, we have we've set up the structure for configuring the SA. We have not said which of the SAs we're going to use. Now remember, there's 4 of them, and they're numbered SA0, SA1, SA2, SA3. I should have said named, not numbered. And so when you open one is when you say which one you're using, and here's the function called the SA0 open. That 0 right there is how you indicate which of the 4 SAs you're using. And all these other zeros that you see and all these other SA function calls, they all match. That's how you keep them all together. The names are all SA0 something. If you were, say, to use SA2, then instead of all these zeros, you would see SA2 in all these places, okay? So that's how that works. That's how you specify just exactly which SA you're working with. So we've set up the parameters, and with this call right here, SA open, we've opened it. The SA0 is open, ready for business, ready to go to work. Okay. Now, lines 18 and 19 are adding up all the integers 4 at a time, conceptually doing the same thing as is done on the left over here, okay? You see this SA0 advanced function call. I don't want to explain it just yet because it's a little bit more complicated than this one here, SA0. This one's a little more basic, so it makes more sense to start here. So let me explain this one. I'm going to carefully highlight my goodness, I'm sorry. I'm going to carefully highlight just some of this code, okay? Oh, wait, I see what I did wrong. I moved that parenthesis by mistake. I apologize. There we go. So, I'm going to carefully highlight this code. And I want you to notice that I did not include the asterisks in this. So, for right now, we're not considering the effect of the asterisk on the expression. We're just looking at the function call and its arguments. And the arguments are a type and a base address. And the base address comes from, here, the pointer to the function that was passed in when you called it. And that's why you don't have the analog to pointRI4. All right, it's always, we're using it here, we're using it here, and you never need the equivalent of pointRI4 in this code on the right. So what SA0 does, this expression, it says to the SA, I want to take the current offset, whatever that may be, add this base address pointer to it, that forms an address. Okay? And what is the type of the address? It's this type right here, a pointer to int4. So a pointer to a vector with 4 integer elements. Okay? So once you've got that address, then you use the asterisk operator to, in this case, load it, read the memory location, and copy its value to this variable here, last value I4, also a vector of 4 integers. All right, so that's what this line 23 does. Okay, SA0, the ADV stands for advance, does the same thing, but it also advances the SA to the next offset. Okay, so this is how we're walking through the array of integers 4 at a time with these successive calls to SA0 advance. Okay? Now we can talk about the code on line 22 through 24. It is doing the same task as you see on the left, lines 22 through 23, but we do it the SA way. The SA, in addition to computing offsets, it can also compute predicates for you. You can ask for what is the predicate given the current offset scaled by this type, int4 here. And then in this case we copy it to this variable here, and then that variable is used, that predicate is used in this select intrinsic to choose between values from last value I4 or 0, and that's what gets added into the last for the last accumulation in the sum I4. This is followed by closing the SA, pretty straightforward, and then the last bit is the adding up. It's the same in every example in this video, so I'm not going to talk about that. So that's our first look at using the SA. To try and flesh it out a little bit more, what I'm going to do next is add a little bit of code on the left to make it act a little bit more like the SA. It won't be entirely the same, but it'll be a little bit closer, and it might, well, I say it might, I'm confident it'll improve your understanding just a bit more. So I'm going to add this variable, initialize it to 0, and then in the loop I'm going to get rid of this like that. We don't need this asterisk now that we're using the brackets in the array. And then we say SA0 plus 4, because now we have two statements in the for loop. Gonna put braces around it like that. And then in here, change this to SA0. And remove that asterisk. Okay, so this actually, the code on the left is actually not strictly legal C code now, because the type of this guy is a pointer to int. It's not a pointer to 4 integers, which is what it needs to be. And same thing here. So I need you to view this as pseudocode. I don't want to take all the trouble to cast and create new variables and whatever else it is. So at this point, you can see how the code on the left is closer. Okay, so initializing this guy to 0 is a little bit like configuring the SA and opening it. Okay, this use of, pointer plus SA, the computing address, and then get its value, add it to sum_i4. It's pretty close to what this is doing. Okay, and then we advance after we've done that. All right. And this is like, reading the SA for that last time in the select intrinsic. It's similar to what's happening here. Okay. I'm sorry, this one, that one there. All right. Now the SA0 vpred, I don't have that over here on the left. To model that would take multiple variables and stuff, and I think I've made my point by now. I hope that by setting up the SA here and then using it as an index against pointer like that. And by the way, notice that pointer I4 has disappeared. It's not used on the left anymore. So comparing these two should give you a pretty good sense of how the SA works in this context. So next I want to close example 1. And this will give you a pretty good look at all of the code for example 2. And for those of you who would like to have a screenshot of it, this is a good time to do that. I want to review the SA interface introduced in the second example. So this is a type name. It's a structure type. An SA is configured with the fields from this structure type. The function SA0open takes one argument, a parameter structure. What it does is it opens SA0 and configures it with those parameters. The function SA0 has two inputs, a type and a base pointer. What it does is it returns the current SA0 offset plus that base pointer. That's an address. It is casted to a pointer to type, whatever that is. And remember, in our example, it was always int4. And then it is usually combined with the indirection operator asterisk to perform a read or write. In this case, in our example, it was a read. Okay, SA0 ADV stands for advance, has the same inputs and returns the same result as SA0, but it also advances SA0 to the next offset. SA0 vpred takes a type as an input and it returns a predicate for the current SA0 offset, scaled according to type. And remember, in our example, type was always int4. All right, SA0 close is pretty obvious what that does. Every operation that I showed that had SA0 in the name has variants for SA0, SA1, SA2, and SA3. So there is an SA3 vpred macro, for example. I want to close this video with two references. The first one is to this long web address here. If you don't want to type that in, I can understand. I recommend that instead you search the internet for the term C7000 compiler. I've tried that search with a few different search engines. I always got this web address as the first result. However you get there, you're at the home page for the C7000 compiler. It's where you can download the compiler, access the manual, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If your question is related to the compiler, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.